Hey guys, in today's video we're going to be going over answers in Genesis Canada. They made a video called This One Thing Will Make You Believe in Noah's Flood. It is 2 years old, but I figured I'd go over it now because might as well go over it. The first topic is going to be about physical evidence for geological processes.
Everyone accepts that fossil-laden rock layers cover the continents, and most of these were laid down by water.
While sedimentary rocks do cover much of Earth's continents, the scientific consensus firmly establishes that these layers formed over hundreds of millions of years through diverse geological processes, not a single catastrophic flood. The Grand Canyon's geological records span approximately 1.8 billion years, with the visible sedimentary layers representing roughly 500 million years of Earth's history. Modern geological dating using radiometric methods, including UPB and REOS geochronology, provides precise ages for these formations. For example, the Quar group in the Grand Canyon has been dated to approximately 729 to 757 million years ago, and if I pronounce that wrong, I pronounce that wrong. I don't know how to pronounce all these things. I'm not super genius at this. The International Chronostratigraphic Chart maintained by the International Commission on Stratigraphy documents the standardized geological timescale based on thousands of measurements worldwide. Rather than uniform water deposition, these rocks show evidence of diverse depositional environments, including deserts, shallow seas, deep ocean basins, and river systems, each with distinctive sedimentary signatures that contradict a single flood event. As you can see for this first chart, it is the International Chronostratigraphic Chart showing geological time divisions with numerical ages and stages relevant to sedimentary rock layers and fossil formation. This next chart I'm showing you is the geological cross-section showing stratigraphic layers including Tapiat sandstone, illustrating rock distribution and layering in the Grand Canyon area.
The physical features of the Earth's terrain clearly indicate a catastrophic past, from canyons and craters to coal beds and caverns. Some layers of strata extend across continents, revealing the effects of a huge catastrophe.
Contemporary geological research demonstrates that Earth's topographic features result from slow, ongoing processes operating over geological timescales, not catastrophic flooding. Canyon formation occurs through gradual river incision over millions of years, as evidenced by the studies of Colorado River system, which show incision rates of mere millimeters per year. The Grand Canyon itself formed through approximately 5 to 6 million years of Colorado River erosion, with canyon evolution controlled by channel hill slope, feedbacks, and base level changes from river integration. Coal beds form through the gradual accumulation of plant matter in swamp environments over thousands to millions of years, requiring specific anoxic conditions that preserve organic carbon, which is a process incompatible with rapid flood deposition. Cave formation occurs through chemical weathering of carbonate rocks by slightly acidic groundwater over tens of thousands to millions of years. Modern process studies exemplified by research on lava dam formation and removal in the Grand Canyon show that even relatively rapid geological events occur over thousands of years, not days or months.
Another example, which tourists can visit around the world, is rock layers that were deposited around the globe at the same time. This is consistent with the Genesis account of a worldwide versus a regional catastrophe. For example, the Tapiat sandstone, which sits on the basement rocks of Grand Canyon in Arizona, also appears far away in Wisconsin and across the ocean in Israel and Libya under different names. How could a local flood deposit the same rock layer across multiple continents?
The global occurrence of similar rock formations reflects the principle of sequence stratigraphy and eostatic sea level changes, not simultaneous worldview deposition during a single flood event. The Tapiat sandstone and its co-relative represent the Great Unconformity, a major erosional surface that developed over hundreds of millions of years during the Neoproterozoic period. Recent research on the Great Unconformity demonstrates it formed through prolonged glacial erosion during snowball Earth events approximately 717 to 635 million years ago, followed by transgressive marine deposition as ice sheets melted. These formations appear on different continents because they formed on the same continental masses before plate tectonic movements separated them. The Tapiat sandstone correlatives reflect deposition on the margins of the supercontinent Rodinia. Radiometric dating shows these formations have similar but not identical ages, spanning millions of years rather than representing simultaneous deposition. The correlation of these units across continents actually supports plate tectonic theory and long-term geological processes rather than catastrophic flooding. This graph here is a cross-sectional geological map showing sedimentary rock layers and geological periods from Precambrian to Cenozoic across west to east regions, illustrating continental scale rock layer correlation. Now for the topic of fossil formation and preservation.
In contrast to the slow, standard evolutionary story of deposition of sediments making fossils slowly over hundreds of years, in reality, creatures must be buried rapidly before they rot or get eaten by scavengers. And in fact, vast numbers of animals were buried and fossilized so quickly that some couldn't even finish swallowing their meal or giving birth.
Scientific research on taphonomy, the study of fossil preservation, reveals that exceptional preservation occurs under specific geochemical conditions, not necessarily rapid burial. The famous Burgess shale fossils, which preserve soft tissues of 505 million-year-old organisms, including jellyfish, demonstrates that exceptional preservation results from rapid entombment in fine-grained sediments under anoxic conditions that prevent decay. However, experimental taphonomy shows that organisms can be preserved for extended periods of time before final burial if environmental conditions inhibit bacterial decay. Studies of modern marine environments demonstrate that microbial mats can preserve organic remains for months to years by creating protective psychrophagy around carcasses. Research on fossil embryos show that preservation can occur over sufficiently long periods for mineralization without requiring instantaneous burial. The key factors for exceptional preservations are anoxic conditions, rapid sealing from oxygen, and specific sediment chemistry, not the speed of a catastrophic burial event. In this next graph, you will see that footprints are left in the mud, and then next you will see that the dinosaur collapses and dies. After some time, the flesh rots away, bones remain. After some time, the water level raises, and sediment buries the bones and footprints. After some time, a thick sequence of sediments accumulate over the bones. Gradually, the bones fossilize. Over some time, this bed now contains the dinosaur bones. Now, over some more time, erosion exposes the layer of strata containing the bones and footprints. This is just basically an illustration of the fossilization process, showing how dinosaur remains and footprints become fossilized through sedimentation and burial over time.
And we also have multiple examples of soft-bodied creatures like squid, octopus, and even jellyfish, which turn to goo in a matter of days once they die, being perfectly preserved, certainly not the result of some slow geological process, but rather evidence of rapid burial and fossilization indeed.
The preservation of soft-bodied organisms represents well-understood taphonomic processes that occur under specific environmental conditions over extended time periods. The Burgess Shale and similar deposits preserve soft tissues through a complex process involving rapid entombment in fire-grained sediments, followed by mineral replacement under anoxic conditions. Research on 505 million-year-old chitin preserved in Burgess Shale sponges demonstrates that organic molecules can survive for hundreds of millions of years under appropriate geochemical conditions. Studies of the Chenjiang biota show that different animal groups have varying preservation potentials, with some tissues more likely to be preserved than others based on their biochemical composition. Experimental studies using modern arthropods and mollusks show that preservation quality depends on sediment mineralogy, with kaolinite-rich sediments providing optimal conditions for soft tissue preservation. The exceptional preservation of these deposits occur in specific depositional environments characterized by low oxygen levels and fine-grained sediments, conditions that can persist for thousands of years without requiring catastrophic burial.
Another obvious evidence that makes sense in a global flood is fossils of tree trunks, some of them 30 feet tall, standing upright or upside down through one or more layers. This doesn't make sense with the slow accumulation of layers over millions of years, but instead, it's a sign that these polystrate fossils were buried rapidly.
Upright fossil trees, known in geology as polystrate fossils, are well-documented phenomena that form through normal sedimentary processes over decades to centuries, not evidence of rapid global deposition. Historical geological studies from the 19th century documented upright fossil trees in carboniferous coal measures, showing that these formed in ancient swamp environments where trees grew and died in place as sediments gradually accumulated around them. Modern studies of coal-forming environments demonstrate that peat accumulation can bury standing trees over periods of 50 to 200 years while preserving their upright position. Research on early tree growth reveals that ancient trees had unique structural adaptations that allowed them to survive partial burial for extended periods. The preservation of upright trees requires specific depositional conditions, typically in swamp or floodplain environments where episodic flooding brings sediment that can bury the lower portions of trees while they remain alive. These deposits form over thousands to tens of thousands of years as river systems migrate across floodplains, creating the appearance of trees extending through multiple layers, but actually representing trees that lived during different phases of sediment accumulation. In this graph here, polystrate fossilized tree trunks are extending through multiple sedimentary rock layers, which illustrates rapid sediment deposition. In this other diagram of polystrate trees, it shows upright and inverted logs extending through multiple sedimentary layers, illustrating rapid burial in geological strata. For the next topic, we're going to be going over marine fossils and continental interiors.
We find fossils of sea creatures in rock layers that cover all of the continents. For example, most of the rock layers in the walls of the Grand Canyon, more than a mile above sea level, contain marine fossils. Fossilized shellfish are even found in the Himalayas.
The presence of marine fossils in continental interiors and at high elevations provides compelling evidence for plate tectonics and mountain building processes operating over geological time, not evidence of a global flood. Marine fossils in the Grand Canyon formed when this region was covered by shallow seas approximately 250 to 500 million years ago, long before the Colorado Plateau was uplifted to its current elevation. The Grand Canyon's marine fossils occurred in specific stratigraphic intervals that correspond to transgress marine sequences when global sea levels were higher and continental margins were flooded. Marine fossils in the Himalayas formed when the sediments were deposited on the floor of the Tethys Ocean before the Indian subcontinent collided with Asia beginning approximately 50 million years ago. The process of mountain building through plate collision elevated these former seafloors at sediments to their current high-altitude positions over tens of millions of years. Similar marine fossil occurrences in other mountain ranges worldwide, the Appalachians, Andes, the Alps, all show the same pattern of ocean floor sediments elevated through tectonic processes. The distribution and ages of these marine fossils correlate precisely with the timing and patterns predicted by plate tectonic theory, providing strong evidence against their formation during a single global flooding event. For the next topic we're going to be talking about is going to be continental rock layer correlations.
The Grand Canyon also contains multiple flat layers that are sitting on top of one another, without any evidence of erosion in between. Evolutionary inclined scientists believe these were deposited millions of years apart, and in fact, other deposits were laid in the interim in other places. For example, the Coconino Sandstone sits directly on top of the Hermit Formation, but there's no indication of any layer deposited between these two layers seen elsewhere. Supposedly, 5 to 10 million years passed before the Coconino Sandstone was deposited on top of the Hermit Formation without evidence of any erosion. The Coconino looks like it was in fact deposited immediately on top of the Hermit. Wouldn't you call this evidence for a global flood?
Detailed geological studies of Grand Canyon stratigraphy reveal extensive evidence of erosional unconformities and in missing time intervals between rock layers, contradicting claims of continuous rapid deposition. The Great Unconformity at the base of the Grand Canyon represents approximately 1.2 billion years of missing geological time, where Cambrian sediments rest directly on Precambrian basement rocks. Recent research demonstrates that this unconformity formed through prolonged erosion during Neoproterozoic glacial events, removing vast amounts of rock over hundreds of millions of years. Between the Hermit Formation and Coconino Sandstone, geological evidence shows a significant time gap, with evidence of subaerial exposure, soil formation, and erosion before deposition of the overlying unit. Modern geological mapping identifies numerous unconformities throughout the Grand Canyon sequence, representing periods when deposition ceased and erosion removed previously deposited materials. The flat appearance of contacts between formations results from later tectonics tilting and erosion that has preferentially removed softer rock while preserving resistant layers, creating the illusion of conformable deposition. Radiometric dating confirms that millions to tens of millions of years separate the formation of adjacent rock units in the Grand Canyon sequence. The next topic is bent rock formations.
Or how about this one? You can go to many places on the planet and see row upon row of consecutively deposited rock layers that were soft when deposited and then bent, sometimes drastically. Rocks don't normally bend, they break because they're hard and brittle. But in many places we find whole sequences of strata that were bent without fracturing, indicating that all of the rock layers were rapidly deposited and folded while they were still wet and pliable before final hardening. The Tepete Sandstone in Grand Canyon is folded at a right angle without evidence of breaking. Yet this folding could have only have occurred after the rest of the layers had been deposited, supposedly over 480 million years, while the Tepete Sandstone remained wet and pliable.
The formation of folded rock layers without fracturing is a well-understood geological process that occurs through ductile deformation under specific pressure and temperature conditions over millions of years. Rocks can deform plastically when subjected to elevated temperatures and pressures deep within the Earth's crust, allowing them to fold without breaking even when completely lithified. The folding of the Tapiat sandstone and overlying formations in the Grand Canyon resulted from regional tectonic stresses associated with the formation of the Colorado Plateau, occurring approximately 70 to 50 million years ago. Laboratory experiments demonstrate that even brittle rocks can deform plastically under conditions of high confining pressure and elevated temperature, conditions that exist several kilometers below Earth's surface. The complex folding patterns observed in mountain ranges worldwide require sustained tectonic forces operating over millions of years to produce the observed structural geometries. Metamorphic studies of folded rocks show evidence of recrystallization and mineral alignment that develops only under prolonged elevated temperatures and pressure conditions. The absence of fracturing in folded sedimentary rocks indicates that deformation occurred under deep burial conditions, not during soft sediment deformation immediately after deposition. Thank you guys for listening. I hope you have a good day. If you have any questions, just ask them in the comments, and I apologize for my pronunciation of a lot of these words. It was a lot of work and it was a lot of reading, but I hope you guys have a good day, and I will now head out.